Hello everyone. Now let us discuss rational numbers and their decimal expansion. We all know that rational numbers are the numbers which can be represented in the form of p by q, where p and q both are integers and q is not equal to 0. Well, we have also discussed that decimal expansion of the rational number is of two types. First is terminating decimal expansion. The second is repeating and non-terminating decimal expansion. But how will we find that the rational number is terminating or has non-terminating and recurring decimal expansion? So here we have the number 0.375. 0.375 has a terminating decimal expansion. 0.375 can also be written as 375 upon 1000. It is equal to 375 upon 2 into 5 to the power 3. That is equal to 375 upon 2 to the power 3 into 5 to the power 3. So here we can see that how this 0.375 is represented as 375 upon 2 to the power 3 upon 5 to the power 3. Let us take one more example. If I take the decimal number 0.0875, 0.0875 can be written as 875 upon 10,000. This can also be written as 875 upon 2 to the power 4 into 5 to the power 4. So this was the terminating decimal expansion. If I take the numbers, that is 10 by 3, which is equal to 3.33333 and so on. 10 by 3 can also be written as 10 upon 3 to the power 1. This means it has non-terminating and recurring decimal expansion. Similarly, if I take example of 43 upon 36, which is also equal to 43 upon 2 into 3 to the power 2. That is equal to 43 upon 2 to the power 2 into 3 to the power 2, which is also a non-terminating and recurring decimal expansion. So here we have two types of example. In first example, the decimal expansion was terminating, and in second type of example, the decimal expansion was non-terminating but recurring. Here we have three theorems to identify if the decimal expansion is terminating or non-terminating and recurring. So here we have the first theorem which says let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form of p by q, where p and q are co-prime numbers and the prime factorization of q is of the form 2 to the power n into 5 to the power m. So here let us take an example, understand this theorem. So if I take 19 upon 125, which can also be written as 19 upon 5 to the power 3. If I multiply and divide this by 2 to the power 3, this will become 19 into 2 to the power 3 upon 2 to the power 3 into 5 to the power 3, which is equal to 152 upon 1000. That means it can be written as 0.152. So here we can say that the ratio of the numbers will have terminating decimal expansion if the prime factorization of denominator is of the form 2 to the power n into 5 to the power m. So here we have the second theorem which says that let x is equal to p by q be a rational number and the prime factorization of q be of the form 2 to the power n into 5 to the power m. Then the decimal expansion of this rational number will always terminate. That means if I take the example of 0.175, 0.175 can be written as 175 upon 1000. It can also be written as 175 upon 2 to the power 3 into 5 to the power 3. That means we have seen that if the decimal expansion terminates, then the prime factorization of the denominator will always be of the form 2 to the power n into 5 to the power m and vice versa. Similarly, let us understand the third theorem, which is about the non-terminating and recurring decimal expansion rational number. The third theorem says that let x be is equal to p by q, where the prime factorization of q is not of the form 2 to the power n into 5 to the power m, where n and m are the positive integers. Then the decimal expansion of this number will always be non-terminating and recurring. For example, if I take number 10 by 3, 10 by 3 which is equal to 10 upon 3 to the power 1, or if I write this in decimal form, I will get 10 by 3 is equal to 3.33333. Therefore, we can say that if the prime factorization of denominator, that is q, is not of the form 2 to the power n to 5 to the power m, then it has non-terminating and recurring decimal expansion. We take one more example, which is 100 upon 33, which is also equal to 3.33333.